Next up we have Christian Dimitrescu and Jasvinder Singh who are going to talk about the quality of service, APIs, etc. So, thank you.
Hey guys. Do we have...
There.
Okay. So we have quite a few things to talk to the world about today. Maybe too many topics for half an hour. We'll try to see how much we can make progress. We want to talk about a couple of new APIs that we added in DPDK recently, or we are trying to add. One of them is about traffic management. It's already part of DPDK since release 17.8. It's an API that was developed in collaboration with our friends from Cavium and NXP. The other API is the sister API is still part of the same quality of service feature set. It's the metering and policing API. This is work in progress at this point. We already sent V1 on the list, and we are still we still need to do a bit more work, so V2 is pending there. And then last but not least is the topic of software equivalency or software fallback for a bunch of these Ethernet APIs. What do you do when your NIC doesn't really support these features, but you still want to write your application in a way that is agnostic about the implementation? So this is about doing software fallback for these ETEV APIs. We start with the traffic management because that's how the whole thing started, but it went into a discussion that is quite complex, and let's see how far we can go today. So traffic management. What this really is about hierarchical scheduling. It's about that point on your TX pipeline. Just before you send packets, you really want to manage the bandwidth of the output port. Maybe you need to send more packets that you can physically push on the bandwidth. So then you need to prioritize. We already have a library in DPDK called librtschedule, which is doing hierarchical scheduling for a specific hierarchy, very much tied into edge routers. This API is actually a generalization of that. It supports lots of other features. That library could be used as the software fallback. We'll talk about it again when we talk about the SoftNIC. Why doing an API for these type of features? Well, the answer is because it's yet another generic feature of Ethernet devices, whether that device is a CPU, whether it's a NIC or an NPU, an FPGA or an ASIC or whatever, whether it comes from one vendor or the other, whether it's done in hardware purely or in software or a mix between hardware and software, we tried to create a generic API so that you get your application to be agnostic about the implementation. Again, this is already included in DPDK. The header file is RTTM, is yet another extension to the ETHDEV API, similar to the Flow API, similar to RT security that we just talked about. So in terms of features, we have a bunch of API. Do I have a pointer here? No. So we have a bunch of APIs to get the capabilities of that device. By the way, I think that's something that we should actually do for all these new APIs that we introduce in DPDK. Maybe looking at Thomas right now. So whenever we introduce a big API, we should also have a capability, a way to actually query, see what exactly is implemented there in hardware. And this is the idea that Jerin was very adamant about, and all the credit goes to Jerin for this. In terms of scheduling, we implement strict priority and weighted fair queuing algorithms. Which is the button? Okay. Okay, yeah, should. Yeah, it's working here, not here. Okay. Thank you. Okay, so In terms of traffic shaping, basically this is a rate limiting. We support the dual rate shapers, single rate shapers. Congestion management, tail drop, head drop, and weighted random early detection, and packet marking as well. So this is the standard set of features that we have a part of this API. It's quite a big API. So maybe next go to Jasvinder.
Hi. So how to use this TM APIs, which Christian was describing, to build a hierarchical scheduler. So hierarchical scheduler is built around the physical interface, and this hierarchy has basically two type of nodes, leaf nodes and non-leaf nodes. The leaf nodes sits on top of the packet queues of the hardware devices. So their IDs are derived from the packet queue IDs of the hardware devices. So in other words, they are predefined. So for non-leaf nodes, which are above the leaf nodes, their IDs has to be determined by the applications, and this should be outside the range of leaf nodes. So in nutshell, each node has, in the hierarchy, should have a unique ID, which could be used to update the configuration or to change some of the parameter when needed. So each of the hierarchy node has either a 0 or one private shaper and 0 or multiple shared shaper. So private shaper, what is that? So private shaper basically perform the rate limiting or shaping of the traffic for a single node. So that is private shaper, while the shared shaper perform a traffic shaping on the group of nodes. So instances of the private or shared shaper in the hierarchy could use any of the profiles, which could be, for instance, single rate shaper or dual rate shaper. So single rate shapers basically use single token bucket where committed bucket is disabled, and in dual rate shaping, we enable both of the buckets, but the rate of the peak rate of the bucket is greater than or greater than 0 or greater than the committed rate of the second bucket. So these are the shaper profiles which needs to be configured carefully while constructing the hierarchy. In terms of WRET context, so for the leaf nodes, each leaf node could have 0 to 1 private WRET context or 0 to multiple WRET context. So WRET is basically weighted random early detection algorithm, which is used for congestion management. Of course, there are other congestion management algorithms, as Christian described, that is supported by the APIs, tail drop, which in case of congestion, start dropping the packet from the tail of the queue, and there are other congestion like head drop as well supported by the APIs. So if we look at this small hierarchy, each of the non-leaf node has single output and multiple inputs. So in the runtime, it arbitrates its input using a scheduling algorithm such as strict priority or weighted fair queuing while observing the traffic shaping set on that node. So this is how the packets are processed through this node. On this side, I'm showing some of the high-level steps which user can use to take a node that when he's trying to construct an hierarchy around the physical device, which becomes the root node of the hierarchy. So first two steps are basically the hierarchy specification phase, which in this phase we invoke successively the shaper add APIs which add shapers or nodes into the hierarchy, and these two steps are run for all the nodes. Like it depends how many nodes we want to add or we want to build the hierarchy with. So once all nodes are added, so first node which we add is the root node, and then all the nodes what we add is become the descendant of that root node. So hierarchy is constructed from top to bottom. So once all the nodes have been added, we switch to hierarchy commit phase, basically. In this phase, we perform the validation. It is expected that driver or the implementation of the API should perform the validation, whether the specified hierarchy is compatible with the specific implementation or not. So once this validation is done, the second phase in this hierarchy commit phase is translation of the hierarchy specification into the implementation specific data structures. So basically creating a blueprint of the hierarchy. And once it is done successfully, there is no error observed, then we can start the port and the hierarchy will get enabled, and then packet will be scheduled accordingly as per the nodes.
Okay, thank you. So this is about the sister API, about metering and policing. This is work in progress. I think we sent V1 and we have some comments pending. We are going to send V2 soon. It's about metering and policing. That's on the RX side. So basically, packets go in and you just try to match them according to a predefined service level agreement. So let's talk about the flow. And you would like to make sure that you award 1 megabit per second to that flow. So whenever packets whenever you get more than 1 megabit per flow worth of packets for that flow, you need to start doing something. So typically they work with 1 or 2 token buckets. We have RFCs there. So you specify you specify usually 2 rates, like a committed rate and a peak rate. And whenever packets are less than committed rate, they are colored as green. Whenever they exceed the committed rate but below the peak rate, they are yellow. And whenever they exceed the peak rate, those packets are going to be colored red. So that's the metering side of things. Is regulated by those RFCs over there. That are basically the metering algorithms that we support. The next operation here as part of the metering is a policing stage. So what the policer could do is obviously execute an action depending on the color of the packet. So you could actually drop the packets. Typically all the red packets are dropped. You could recolor the packet. You could basically override the color that was assigned by the meter stage. You could recolor all the yellow packets as green. That also can be marked into the packet. As we saw from the previous API, there is a packet marking capability there. The other action is basically don't do anything. Obviously, we have statistics for each color. We can decide whether we want to compute number of packets that were colored with that color or number of packets that got dropped because of the policer. So that's the metering and policing API. So now I think we want to go to the last topic and we wanted to save some time to go through this. There are some open questions here that we want to address. So this is about the SoftNIC. So Jasvinder, please.
So SoftNIC, so at high level, the SoftNIC is basically a software augmentation of the NIC that does not support the desired feature. So in the context of DPDK, it is intended to provide the software fallback for the feature not present in the NIC. Currently, it implements TM APIs, but the mechanism is very generic and it could be extended to implement some of the more APIs on the RX side, such as flow or policing APIs. So it can easily, there is infrastructure in place there. So this device is very generic. It can work with any hardware NIC. It does not change any of the feature of the hardware. Instead, it just augments some of the features which are not present in the NIC. So what the SoftNIC does is, for any hardware device, it creates a soft port as a virtual device, which drive the hard port. So in terms of once device is created, the application is free to choose any of the feature. So and these features can be enabled through a special argument passed through during the device creation. The device could be created using EL command line or through later in the application through VDAV APIs. So user is free to select any features which it wanted to enable on the soft port. And once these features are enabled and device is created, that the application needs to configure this device along with the hard port. So there is no step like one does not need to configure the hard port. So application has to configure the hard port as well as the soft port as per the requirement. And once this is configured in the runtime, the application send or receive packet through the soft port because it has some of the features enabled. For instance, it has QoS Scheduler on the transmit side. So that will perform the traffic management on the egress side. So this SoftNIC implements the TM APIs which are generic enough, which hides the implementation specific of any device or the software library. So it fits well in the NFV vision. And this is work in progress, so I'm working on V5 version of this patch set. That's it.
Okay.
We want to take.
So now we want to get a bit into the details of actually implementing a software fallback for Ethernet APIs. As we say here, we just want to do this grand NFV vision here, which is we write an application without, and we put logic in the application about the API, about the feature. We don't put any logic about the hardware device. We don't care which is the hardware device that implements that. It might actually be a software implementation. So, but what I have there is application is almost agnostic about the NIC implementation. So why did we put almost? It's because we have some issues currently with implementing this true vision entirely the way we would like it to be. So this is what we typically want to do, right? This is what we have in the code proposal. So we kind of want to have a skeleton, a Polmo driver skeleton, in there that would enable features conditionally, depending on whether user wants to enable them or not, explicitly saying enable traffic management or not. Again, it started for traffic management, which is basically a feature on the TX side. So we have a hardware device, typically a hardware device, although this could be any type of device, which is basically the underlying device that we want to augment, we want to improve, we want to add support for some features that this hard device doesn't have. So we put a front end, a software front end to this device, and we call it SoftNIC. And basically then the application will read from the queues of the SoftNIC and will write to the queues of the SoftNIC, as opposed to the application reading and writing from the queues of the hardware device. Why do we care about these queues that much? Well, because we all know that basically the reason we have multiple queues for an Ethernet device is because each of these queues might actually specify the features that are applied to the packets that end up to that queue, right? So we have features like Flow API that would direct packets to the queues. We have features like metering and policing, which is basically on top of classification, on top of the Flow API. That would also direct packets to one of the other queues. Same here, traffic management will read packets from these queues. We'll have probably internally a bunch of, a large number of queues, maybe thousands, to where to put the packets. And then, according to the SLAs, they will put packets into the hardware queues of the NIC. So, we have multiple approaches here that we could implement, and this is what we also try to explain, because we had some resistance on the mailing list about this concept. People said, why does this have to be a Polmo driver? Why do we want to implement software equivalency as a Polmo driver? So the alternative would be to put stuff into the glue logic of the Ethernet library, Liberty Ether. So then I'm going to try to illustrate some of the difficulties that we have. So basically, the question is, right now we basically create, the SoftNIC is a different Ethernet device than the hard NIC. And you would say, yeah, this kind of breaks what you just said earlier about the NFV vision, that you don't change the application. Because right now the application needs to know, am I going to talk to the hard NIC or am I going to talk to the soft NIC? So there is a change in the application. Maybe what we hoped is that this change is acceptable, because it's just part of the configuration to kind of say, okay, which is your hard device, which is your soft device for this whatever network interface in your application. So you could use both of them at different times. So we hope that this is acceptable. And the reason we took this approach is because we found a lot of resistance, a lot of things in the Ethernet library that we really have to change in order to do the other approach. So what's the other approach which would be the best approach? The best approach would kind of be hard NIC and soft NIC be the same device, right? So you just have a hardware device that, I don't know, it's not that smart, it misses whatever feature X, and you just have your API call over there as part of your configuration code, or maybe you don't have anything at all. Maybe that happens implicitly, and you just go and augment this device. So you always work with a single device. That is the ideal. But there are a few things that basically, once you start writing this code, you will actually see issues in the Ethernet library. Maybe, I wouldn't say flaws in the library, but there are things that are basically difficult to implement, or maybe a lot of changes to implement to make this philosophy work, which is augment a device. So first of all, what people need to realize is that this is a software construct. Okay, so this needs a CPU core to run. It's not something that will happen automatically. In order for packets to go from this set of queues to this set of queues, or on the other side, from hard to soft queues, you need a CPU core to do stuff, okay? So, first of all, basically there is a run function that needs to be executed here. So how about adding a run function to our ETHDev device to say, okay, run this stuff for me in an infinite loop? Because right now, this is a hardware device. You don't need any CPU intervention for it to run. So that is the first observation. You need a run function to be executed in order for this to work. The other thing is, Thomas was saying on the email list, so thank you, Thomas, for your comments, and I'm going to reply, take my time to reply as well. What is that thread safety requirement? So the thread safety is basically here. Because application is one thread, and the NIC is now a CPU thread. So in order for them to interact, you need a lockless queue here, which is an RTE ring. So what that means in terms of the library, it means that the set of queues have to be overridden, really, because now to apply this feature, let's say this is a single feature soft NIC, we just want to patch one feature. So the hardware NIC, the hardware device has a set of queues, has data structures per queues, but what we need is we need more data structures for that feature, whether it's traffic management or flow or policing. We need another chunk of memory to store those data structures. And we also need to store a data structure per queue as well. This is why we figured we draw those queues there. So basically what we need is per feature to overwrite the data pointer of the Ethernet device and the RX and TX queue pointers for the Ethernet device. So basically, if we want to kind of augment the existing device, what we need to do is have the library offer us another set of data pointer, RX queues, TX queues for that specific feature, so that we could use those to store the data structures for that feature. And now you can also realize the other complication, which is what do we do when we have lots of features? So basically we need to integrate lots of features into a single set of RX queues, TX queues, and data pointers. So those are a few things that where we need to work together and see if there is a better way to improve the library in order to turn this into reality, this approach of augmenting an existing device and making it better with software front ends. So meanwhile, I think we want to make progress here on the traffic management side because we invested a lot of work into making this software fallback there. So probably, if you ask me, but it's just my personal opinion, obviously, we probably need to go ahead with the Polmo driver approach for a set of limited features, and my proposal here would be traffic management on the TX side. Hopefully for the future I would like to do flow API. That's a very critical feature where we need a software fallback and metering and policing. And meanwhile, maybe start a discussion on how to improve the library to make it more generic and accommodate all these changes, all the software fallback into the single library going forward. So I think these are the challenges. I think it's a lengthier discussion and we'll probably not finish that soon. I'm done. So 1 minute left for questions.
Actually, go back to that previous diagram. We could. For the hardware NIC, those blue queues, are those the 8 Ethernet priority queues for that physical device? Is that
these are the hardware queues of the device that you find in the device spec. Basically, they are in memory.
Do they equate to the PFC, the 8 Ethernet hardware priority queues?
So, for example, I think on let's say, pick a random example, Intel NICs, they support 128 queues on reception and 128 on transition for the NAND NIC, which is the old 10 gig NIC.
Okay, all right. And then why do you need multiple queues going into the app? And we effectively would have multiple apps, right? Why aren't we... There's essentially a classifier on the RX side, right? You'd go single queue into the app.
Yeah, I think we should take an example. So let's take the example of flow classification. We want to add a support in the SoftNIC for flow API. What that means is that your hardware NIC doesn't have flow classification API. So basically all the packets actually go to a single queue. Or maybe just to 8 queues, but that's just a priority thing. We don't, they are not able to kind of put different flows to different queues. They just put all the flows into 1 queue or 8 queues, whatever, right? So then you want to improve that device, augment it and make it fix this gap. So then you want to have, let's say, 120 queues, 1K queues, 16K queues, whatever, to put each packet, each flow to a different queue. So how would you implement that in software? That's the idea. So the number of software queues could be actually larger or the same as the number of hardware queues, depending on the features that you want to implement. So do classification, basically all the packets, get all the packets from the hardware queue and put them into a lot of software queues. And let's take another example, you want to do policing. So then based on those flows that go to this queue, when you read packets from this queue, they are also metered and policed. They have a color written in the metadata, or they might have been dropped if they exceeded the SLA, which is not the case if you would read packets straight from this queue. Here, you would read all the packets without any color. So that's the idea.
Okay, because the way I would see it is you'd have 8 blue queues. You go into your, whatever your congestion algorithm is, WRED or something like that. Then you have a scheduler, and then you have a classifier, and you have a single queue going into each application CPU. Because otherwise, you're going to be polling a lot of ports.
Well, I think we are pretty much saying the same thing. This doesn't have to be a single application. This could be a multi-threaded with 1,000 threads. Okay, so it's just a generic application block. This is not necessarily a single thread. Could be multiple threads here.
And then on the transmit side, you'd want to have a single queue per CPU again, and then that would map to whatever hierarchy you have in the TM, and then once it's determined a port, they would go out to the 8 hardware queues for the TX side, right?
Yeah, it's just on the TX side, it's probably a lot more than just 8 queues. But anyway, I don't think that. I think we're saying the same thing. I'm not sure where the difference is.
Okay, we're a little bit behind in time, but maybe just one last.
So the SoftNIC will query the hardware. Thank you. So the idea is that the SoftNIC will query the hardware NIC, what's its capabilities, and it will know what can I push to be hardware offloaded and what has to be implemented in software.
This is one approach. Personally, I'm not favoring this approach. In my opinion, I think the user, the application should explicitly enable features that the SoftNIC should implement. But what you say is also an alternative where this is automatically discovered based on a capability API. Do you, Mr. HardNIC, do you support this feature? If no, I'm going to take over. So that could be implemented in a pull mode driver or could be implemented in the library itself, in the glue logic of the library. By the time the real API is called, all this querying has happened already and we do the right thing.
So currently the implementation is that the application queries the hardware PMD and the software PMD and decides what to
My
configure?
opinion is that this decision should be taken by the application as opposed of the library doing this automatically, trying to be smarter than the application. But I'm not saying this is the only way it could be done.
Okay. Thank you very much, Christian, Jaswinder.